Good afternoon, everyone. Welcome to the session Disruptive Networks. This afternoon we will have three presentations that has a certain aspect disruptive to the current networking aspects. So that's why the session titled Disruptive Network. Our first presenter will be Karel van der Veldt, who is working in his PhD at the University of Amsterdam. He obtained his master's in computer science at University of Amsterdam and his bachelor in computer engineering at Hogeschool van Amsterdam. His research interests are green computing and networks and data centers and high performance and distributed computing. His current presentation will describe carbon-aware path provisioning for NRENs. Karel, please give your presentation.
Okay, so hello, I'm Karel van der Veldt from the University of Amsterdam, and this presentation is about carbon-aware path provisioning for NRENs. And we did this in collaboration with Energy Science Network and SurfNet. So carbon-aware, this is about investigating networks and finding out researching if we can reduce the carbon footprint of NRENs, of computer networks, because the ICT sector uses contributes approximately 3% of the global carbon emissions, and in the near future may overtake the aviation industry, which means that the ICT industry as a whole uses quite a lot of is responsible for quite a lot of carbon emissions worldwide. So how can we reduce the carbon footprint of computer networks? That is what this is about. So the research question is, how can you accomplish green path provisioning with the goal of reducing overall carbon emissions in the network? So and also if you can if that makes any sense at all, is that possible, and how can you can there's also a monetary aspect to it, like related to it, because you could reduce the carbon emissions. You could also look at reducing energy costs, which are related to each other. So, and this is about circuit switching, so not IP packet switching, and some definitions. So with green path, I mean a path that if you have, if you have two endpoints and you want to send transmit data between them, well, then there may be more than one possible path, and then the question is which path should you take so that you cause the least amount of CO2 impact. And cheapest path, the one that causes the least amount of energy. So the current situation in NREN networks is that most networking devices consume a constant amount of power regardless of traffic, which means that in current networks you cannot really reduce the energy consumption or the carbon footprint at all, because no matter what you do, all the devices consume the same amount of power anyway. Except if you shut down parts of the network, but there are problems with it because then you change your topology, and also you have to decide somehow when you should turn them back on, which means you have to anticipate when you have to anticipate traffic beforehand. So more preferred situation would be that you have networking devices that can adjust the power consumption depending on traffic load. And for example, there's one standard already, energy efficient Ethernet, which is a protocol that is used to shut down interface ports on routers and switches and such, depending on the amount of traffic that there is. If there's no traffic, then you can shut them down. This is somewhat limited because interface ports only consume about 5 watt per port or something, so it's very low. So the amount of energy you can actually save is limited. So then the question is, okay, does it make sense to investigate further in these kinds of technologies, energy-saving technologies, and how much can you gain from that, as well as the green pathing that I will explain more in a moment. So I have 2 use cases. First case is ESNet. So I investigated did this research on several networks. The first one is ESNet. Here you can see a subset of the ESNet topology, layer 3 network only. I mean only the layer 3 devices. I collected the power from all these devices. It turns out that they always consume the same amount of power, as I explained before. So, and the question is, how can you use these energy efficient technologies to actually? How could you use energy efficient technologies to reduce the carbon footprint? Second use case is SurfNet. I should mention that ESNet covers the whole United States, so almost all these nodes are in different states. And SurfNet is much smaller. It's only mostly in the Netherlands. Also, the topology is level 1 and level 2, and not level 3. Also for each device, this is also a subset of SurfNet, so not the whole thing, but a decent chunk of it. I also collected the power from each device, which each device also consumes a constant amount of power in reality. So I want to show a short demo to illustrate the idea. I hope it works. Yeah. Oh. Yeah. So this is, for example, this is ESNet, and now I'm going to. I can see here I chose the shortest path from this node to that node. This is in New York and this is in California. So then the question is, okay, if you have here in this very simple demo, it shows only. Suppose you're the only user and you want to send in this case 1 terabyte of data from point A to point B. Which path should you take, right? So in this is the current situation. So the devices have no power dependency at all. So no, they're not energy proportional. So if you see here, there's no difference, except that there's a. So suppose the devices are have a certain amount of dynamic power, then you have I wanted to make it a bit smaller, the screen, but I don't know how. That's better, yeah. So now we say that each of these devices, 25% of the total power consumption depends on the traffic load. So you have a base of 75% is always the same, and then 25 depends on the traffic that flows over it. So then you can see that depending on the traffic that is on each node, there are different. You could choose a different path. So this is very simple, and it same sort of thing with SurfNet, but I'll skip that because otherwise the presentation will take too long. Okay. So this is what I just explained. This is what's going on. So you want to transport a certain amount of data from point A to point B. That means you have to, and you want to know which path will cause the least amount of CO2 emission. So you have to know all the paths, and then calculate the CO2 impact for each of them, and then choose the most appropriate one. So the model is then, so each path there, you have to go through a certain amount of nodes, devices. For each of them you have to know the power consumption, as well as the amount of CO2 that is emitted per kilowatt hour in the region where the machine, where the node is located, because the even though a machine might always consume 1 kilowatt, independent of where it is, the actual amount of CO2 that is emitted depends on the region. For example, in Iceland, use mostly geothermal, use a lot of geothermal energy, so then CO2 impact is quite low compared to the Netherlands, where we have much more coal, for example. And I have another slide where the model is more detailed, but I'll skip that because then I have to explain every variable, and that also takes too long. But I can show it if you're interested. Yeah, so here you see energy the emission per region. So in the what I just showed in the topology, so you see that depending on the region, there's a different amount of emission. So that also affects the pathing. So that was the demo, and then the after that I made a simulation of the actual, because the demo is very simple, it's only one path. So in a simulation, I take the topology and then estimate the total amount the total CO2 footprint of the network over time. So there are data is being sent from endpoint to endpoint in the network. And then during a simulation, we take we calculate the total CO2 footprint. The simulation ends when 1 terabyte of data has been pushed through. So then at the end, so there are a number of parameters. So the inter-arrival time between different data requests, the energy proportionality of the router of the devices, the path selection metric, so shortest path, greenest path, or cheapest path, and also the flow type. So short-lived means it only for a short amount of time. Long-lived take a long amount of time to complete. And in uniform, they always take the same amount of time. So you can see the throughput of each type and the amount of data. And in the so this PDF shows that most of the flows are shorter, but there are a couple of the few ones that have a large amount of that are longer, that are a large amount of data. So I did the simulations on ESNet. I get a bunch of graphs out of it. They're all pretty similar, so I'll zoom in on one and try to explain what's going on. So this is the CO2 footprint, would be the CO2 footprint in the current situation. So none of the devices have any dependency on none of the devices are energy proportional. So regardless of what how much traffic there is, they always consume the same amount of power. This is if the whole oh yeah, on the x-axis I should explain first. On the x-axis you can see the energy proportion shows the energy proportionality of the route. So at 0% there is it doesn't matter. But like I just explained, always consumes the same amount of energy regardless. On the other end, at 100%, if there is no traffic, then it would consume 0 power. So that is not realistic, but it's just to show the whole range of possible improvement. And this is the idle. So if there's no traffic at all in a network, that's also just to show the range. So suppose you chose shortest path, but you have devices that are energy proportional to some degree. That is this graph. This line. And the other line shows if you, in addition to using energy proportional devices, also use green pathing algorithm to do the path selection. And from the results, it turns out that the difference between the greenest and cheapest path is very little. So here they actually overlap. And that is in most cases. That's the same in most cases. Yeah, so that's what I just explained. So the improvement you can get also depends a lot on topology and the geographical location of your network, as well as how big your network is. So if it's in ESNet is very spans many different regions, so there's more room for improvement basically than compared to SurfNet. So is it possible to reduce the CO2 footprint of NRENs? Yes, but you need these energy proportional devices. You also have to be able to set up the network, set up network paths directly. So, for example, at the ESNet, Oscars could do that. You use overflow. You also have to have access to the CO2 emissions, so grams of CO2 per kilowatt hour, in order to calculate the actual CO2 footprint. So in the future work, for future work, we want to investigate and compare more NRENs. So right now I'm working on SurfNet as well, in addition to ESNet. Also looking at investigating optimality of networks. So what is the maximum benefit that could be gained using green pathing in these devices? And what you could also ask the question, what would be an optimal topology for minimal CO2 footprint of your network? Also, later on to combine it with a power model for cloud, so that you can have a more holistic view of the whole ICT infrastructure. And implementation in the end. So, okay, so if you think this may be interesting, then we would like you to contact us so that we can collaborate. So what kind of information would we need from you then, if you are an NREN? Well, topology, power measurements of devices, if possible also geographical location. So as I explained, the CO2 footprint depends on your energy sources, which depends on where you are, as well as traffic patterns and distributions. So this is it. Are there any questions?
Any question from? Yeah.
Thanks. Hi, David Wilde from RNet. We've got various legs of our network which run long distances, and some of the sites are solar powered, and the equipment, the batteries and the solar power supplies can report their power consumption and power production. So you could feed that in live, I suppose, dynamically into your calculations. Have you done that, or was the power kind of calculated or ascertained separately, and then you feed it in more statically?
Yeah, at the moment I did it separately, so beforehand, because there's
I know it gets very complicated.
Yeah, it becomes more. But that's what I would like to do. But I don't have enough information to do that. I need to have I need to be able to pull the data from somewhere in order to do that. But yeah.
Any other question?
Yeah, I would argue that we have a very nice distributed system for measuring the performances of these networks called perf sonar. So what I would advocate is that we get a green sonar so that we have a live stream of the power measurements of all the ports and all the devices in the system, similar to perf sonar. Then you can collect the information dynamically in a standard way. So we are working on green sonar.
Okay, thank you for the comment.
Did you talk to any of the equipment manufacturers about power requirements and proportionality of?
No, I have not.
Or do you know which parts of the equipment are producing the most heat, for instance? It strikes me that if you got an IR photograph of the motherboard of a router as it was routing, that you might get some insight into what the proportionality of the power might be. You gave examples of 25% to 100%.
Oh, yeah. You're right.
I wonder what realistic a realistic percentage would be.
That's.
Maybe I can chime in a little bit. We have been talking to Huawei. They have lent us switches which have energy proportionality. So Ethernet switches which shut themselves down given with a certain protocol, which I don't have on the top of my head, if there is no traffic for some time. So your NIC and your Ethernet switch or the Ethernet switch system need to support that link protocol, but then they can do energy proportionality. So we have been doing small experiments with that 1 or 2 years ago. So one other postdoc in my group actually talked with Huawei, that's Jimin Zhao. So we can probably talk offline.
If you can, it may be interesting to approach whatever market central point in the energy market there is in the different countries, because the spot price of the energy may be a useful proxy for the carbon load.
Yeah, I thought about that. It doesn't correspond one-to-one, but I think that there is a relation between the energy price, of course, and the actual energy source. But I don't know how easy it is to correlate between them. Like, if the price goes up by a certain percent, does it mean they're using more coal or more oil or something else? I don't know how you could.
I'll talk you over coffee.
Okay.
So one question from my side also. Did you also consider, or what was your observation, or did you already consider the delay increase of the green path? What is the trade-off of having green and having longer propagational, longer round trip time, for example, for the packets?
Yeah, so latency could increase because you might choose might have to choose a longer path, so then your latency would increase. Yeah, so but
can you somehow measure the trade-off or give a hint for the designer or user to decide which is good for them or which is not, or it's not there yet
it's not really there yet, no.
Yeah, okay. Thank you very much for your presentation.
Yeah,
okay. Our next speaker will be Dimitri Staessens, who has received his master from Ghent University. Then he obtained a PhD on survivability of optical networks. He published over 30 papers and contributed to several European projects. His current interests are the control and management of networks, software-defined networking, and future network architectures. Now he will present a clean state model of a new architecture called Rina. And Dimitri, please give your presentation.
Thank you. So, the title of the talk is The Recursive Internet Architecture, an Opportunity for NRENs to Read Internet Research. It was done with my colleagues from ITUCAT, Edward, Leonardo, and Michael, from Waterford TSSG here, Jason Barron, Michael Crotty, and Francesco Salvestrini from Nextworks in Pisa. Myself, my promoter Didier Kolle, and also my student Sander Reders, who is not here, but he was not working in this project, but also working on Rina, and also in collaboration with John Day from Boston University. So, currently there are some challenges in the current internet architecture. There's weak security. This is the newspaper today. We are looking for some Chinese guys that were apparently breaking into, I think it were 40 sites in the US, stealing economic data. On the other hand, the US isn't completely free of sin. They are scanning our data. There's no QoS support. The scalability issues in the routing system, the number of prefixes that are advertised over the internet is growing exponentially. And the overall system is getting more and more complex, adding more and more middle boxes for firewalls, for carrier-grade NAT, for IP offloading, whatever. There's a lot of functionality added to the current internet that was really not in its original design. So what are the causes? A lot of people say that the requirements have changed. The internet is no longer capable to cope with them. We don't think that's really it. Of course, there are some problems that are related to different requirements, but the main problems like multi-homing, mobility, security, and QoS were just not thought about when the ARPANET was designed. So ARPANET was a promising technology, and it was taken into production very early in its life cycle when Bob Taylor thought of connecting his 3 devices. So he had 3 different terminals connected to 3 different universities. He was thinking, can I do this more simple, to have the same terminal connected to all the 3? I think he thought about it in '68, and the ARPANET was started in '69, so it was only developed for 1 year, and it immediately became a production network. So the current internet has really kept on updating this original design of the ARPANET to keep it running, because it was a production network. It was not something in the lab anymore. So in the 70s, there were computer networking research efforts like Cyclades, the INWG, and they were heading in a similar direction, but they were heading in a better direction, so that they were already thinking about more scalability in the internet. So in 1969, it was 29th of October, the first message that was sent was low. It crashed at the G of login. And the ARPANET was deployed on December 5th, '69. So it began with 4 nodes, quickly expanded to a number of nodes. And in '72, they found one of the first problems, multi-homing. There was Tinker Air Force Base. They wanted connection to 2 different of these IMPs. These were the routers into internet message processors, and they were called for redundancy. So they wanted just a multi-homed connection. And the guys and the ARPANET thought, oh, we cannot support this because we have 2 interfaces in that machine. They have different addresses. There's no way that we can know that they belong to the same host, at least not intrinsically. So we have to build some stuff on top of that. So they thought, okay, we should route to the nodes, not to the interfaces, but let's do this for future work. It's not that important right now. In the meantime, the network is growing, so we have intercontinental connections, specifically to Aberdeen, here to London. Sorry, here's Dublin, but close by to London. And in '76, they saw that they needed to devise something to have all these ARPANET-based networks to build them together, and they have something called INWG 96. It was the International Network Working Group. So there were people from ARPANET, people from Cyclades, people from the National Physics Laboratory in London, some others, and their goal was to design an international transport protocol. They came up with 2 different solutions. One was based on early TCP called INWG 37, and one based on Cyclades in France, called INWG61. So they voted on a synthesis based on these two network architectures, and this was what they came up with. So they had 3 layers of different scope, each with addresses, and this is not what we currently have. So we have so they had a data link layer based on the lowest layer. Then they had a network layer which was based on IMP, so the NCP protocol from ARPANET, Network Control Program. And on top of that, they had an internet transport layer with its own addresses based on TCP. So the ARPANET keeps growing, and on 1983, January 1st, we have Flag Day. So this was the architecture proposed by INWG, and it became like this. So we have a data link layer, which is layer 2, mostly Ethernet, a network layer, a transport layer, but that internetwork layer is gone. So instead of 3 layers of different scope, each with addresses, we had 3 layers, but 2 of them had the same scope, and only 2 have addresses. And to make things work, the addresses are really on the same point. They are naming the interface. So your MAC address and your IP address are basically synonyms for the same thing. That's not really it. So currently we have like 4 layers. That's the simple model that is OSI or TCP. But if you are trying to develop or deploy a network, if you have VPN, so you have layer 2 over layer 2.5 for MPLS. Again, this layer 2 on top, that would be called a pseudo wire. Then you have IP over it, MP encapsulation, UDP, another VXLAN. So the architecture that is this 4-layer architecture is not really what we are deploying. We are stacking these on top of each other in a way that's not that clean. So in 1983, they slide is a little bit off, but so they proposed DNS. So what DNS does is actually giving a synonym. So it's a name, a URL, and it translates to an IP address. An IP address is actually a synonym of an interface of a host. So it's not, they could have named applications so that you say, okay, this is an application, Google Web Server, but they didn't. They just said that this is pointing to an interface on a host, and then you have the port, which is the endpoint of a TCP connection, which is identifying an application that you know which application that it is that's running on that host. So there's a fundamental issue here because you have static binding between layers. Your application is statically bound to your interface, and it's not location independent because it's bound to that interface. So in 1992, they came up with IPv6. So they wanted to resolve the scaling problem in the IPv4-based internet, and there were a number of solutions, and this is very interesting to read on the IETF. It's very nice. They log everything, so if you read the mailing lists there and some RFCs that are there, very interesting stuff. And there were a number of solutions proposed. One of them was Tuba. It's TCP UDP over bigger addresses, which was based on something called CNLP. That's CNLP, I think, connectionless CLNP. Connectionless network protocol, which came from the OSI world. And there was some discussion in the IETF, not really technical, they were more political about who should decide what is going to be done between 2 solutions, one from the Internet Architecture Board, which was this based on CNLP, and another solution was based on an IETF group called ROADS, Routing and Addressing. They did some turf wars. There was another RFC called Poised. I think it was Erik Heuser that came up with that name even. So, and they threw it away and said, okay, we'll start IPNG. And one of the rules for IPNG was that they could not change the semantics of the IP address. So the IP address was going to continue the name of the interface and not the host. And so you still have that multi-homing problem that when you want to route over different routes to the same end host, you really need some additional features to figure out what the addresses are to that host. So what are the fundamental solutions to these problems or these challenges? Well, application names aren't very hard to fix, so you just name your application and you map it to the node name. Quite easy. The application developer doesn't really care about how you call your node. They want to say, okay, if you want to communicate with another application, just say, this is the application I want to communicate with, and let the next network figure out how to reach that application. So that seems simple. It was done like that in Cyclades. It was done in XNS, DECnet. So in the 70s, the solution was known. So multi-homing, same thing, just name your nodes. ARPANET was aware of it, they knew how to solve it, but they didn't. Cyclades network in France solved it, but IPv6 continues to route on the interface. Then, so you should route on node addresses, not on interfaces. So routing should be a two-step process, so maybe I'll use so it should be a two-step process. First, you calculate a sequence of nodes, which is the route to the next hop, and then there's something else that you need to know. Yeah, that won't work. So that you need to calculate a path, because a certain node can have multiple interfaces. The properties, there's an RFC and a paper from Jerry Salter in the 70s that says how you should, it's called a complete naming and addressing scheme, how you should do naming and addressing in a network. So you should name your application, you should name your node addresses, you should name point of attachment addresses, and you should name your routes. So is this the definitive architecture for an internet? Well, you should have these 4 nodes, but actually it doesn't seem so, because you have virtual networking where you have another layer on top of the internet. What about an internet of internet networks? So there doesn't really seem to be a fixed number of layers that can solve all the problems in the internet. So the fundamental internet architecture should be recursive. That's what we came up with. So John Day. So if you put it all together, so this is the recursive internet architecture. It's based on this book by John Day from 2008 or 2009 called Patterns in Network Architecture. And so this is what Rina looks like. So it has a structure of recursive layers that provide IPC, so inter-process communication services to applications on top. There's a single type of layer, so you don't have like an Ethernet. So now the layers are based really on certain technology. You have an Ethernet layer, you have an IP layer, you have an MPLS layer. Every layer has a different scope, but also a different technology. So in Rina, you have a single type of layer that repeats as many times as you require it. It takes a fundamental property that was used in design of operating systems. That's called the separation of mechanism from policy. So the invariant ideas are the mechanisms, and policy are the variances. For instance, if you have a bidirectional forwarding, a BFD protocol is something that supports separation of mechanism from policy. So it implements similar than the hello protocol in OSPF, and it allows you to just set the interval, the timing interval. So all layers in Rina have the same functions, but with different scope and different range. Not all the layers need all the functions, so some you implement, some you don't. And the layer is called a distributed application that performs and manages IPC, so that's why it's called a distributed IPC facility, or a DIF. A DIF is a homogeneous application, so every process that is part of this distributed application running on different machines is exactly the same, except for the policies, but the mechanisms are all the same. And so these are the processes. This is one application providing IPC. This yields a theory and a scalable architecture, and the architecture completely looks like this. I'll step here for a moment. So every system has applications running. It has a management agent which manages all the IPC processes in the system, and each IPC process follows this API. It has these functions. So you have data transfer, you have data transfer control, which is similar to TCP. So it is responsible for transmission control, for retransmission, so for sending ACKs, deciding how long you should wait for an ACK, how many ACKs you should receive, things like that, doing flow control. And there's layer management that is taking care of enrollment, which means that one IPC process joins a diff, so that there is some authentication there. So right now, when you want to join a network, you just configure your interface, you plug it into the socket, and then you are connected to the network. There is no real control there in most networks. In Wi-Fi there is. In Wi-Fi you have to really enroll into the network. In IP you don't, you just configure a correct IP address. If you configure an incorrect IP address, you can actually tamper with the network. So in Rina you have to actively enroll into the network. And the operation phases are thus enrollment. So it's between IP processes. So you create, maintain, and distribute the information required to create the instances of communication. So in IP this would be manual or a little bit Dhcp. Flow allocation is when you have different applications on top. They request IPC functionality to the application, to the diff below, and the diff will check if you are allowed to communicate with the end host. The end host will then reply if he wants to communicate with you. And if all authentication and steps are allowed, then flow is allocated and you are allowed to actually transfer data between the two application processes. So the Ipc API is what in Rina, let's say, similar to the socket API, but it has only 6 operations. So you can register your application with an IPC process to make use of its IPC functionality. You can request to allocate flows between a certain application with a certain QoS. So Rina supports QoS. And you can write and read packets to that certain application or certain diff. So the QoS parameters are defined in a technology agnostic way. There's still a lot of work to be done there to do that correctly, and not that easy. And in order to aid adoption, there's also a full sockets API which just translates socket calls to Rina calls. Another technology is shimdiff. So at the lower layer, you will have to provide the Ipc API either towards the transmission medium or an existing network architecture or an existing network protocol. And that's what we call a shimdiff. So it's just a non-Rina layer in the network as low as possible, where we write a piece of code around it so that it exposes the Ipc API above, so that we can build Rina stack on top of that. So the main duties are to map the n+n layer application names to the addresses in the shimdiff layer, and to allocate and deallocate flows within that shimdiff. So this is a bit example of how you would start a Rina network. So this will maybe clear up a lot of things for you. So first of all, you would start an IPC process in a certain node, let's say in this edge router, and at the lower layer it would be a shim IPC process. So this would be something in the Irati project. We are building it around Ethernet. So let's say that between this here is an Ethernet link, these are Ethernet links, and this is an Ethernet IPC process, which is directly tailored to the Ethernet layer. So in each node you would have a management agent that takes care of all these IPC processes. So once you start a second one on, for instance, this host, which is an internal AS router, they join each other. So the registration would be in our Ethernet shimdiff is done implicitly. It's done when you configure the VLAN. You have a direct connection between those two processes. The two applications can talk to each other, and you have what is called a shimdiff. You do the same on the other hand. Now it becomes more interesting. So you do the same for the edge routers. But let's say we have a normal IPC process. We start it on the border router, and you register it within the shimdiffs below. So now A2 knows that D1, the process D1, is reachable by A2. If you want to build connectivity between the two edge routers, you would start the IPC process on the other two. It's otherwise. So you start an IPC process here, and you would have to enroll the enroll phase with D1. So D2 would ask the IPC processes C1 and A1 if they can reach D1. A1 would respond positively, I can reach D1. So it would then enroll with D1. So it would allocate a flow, management flow between A1 and A2, so that D2 can request enrollment with D1, and if D1 responds positively, they can set up a diff, and D3 can join the same way. So this is how all the layers in the Rina network are recursively built until your applications register with, for instance, the IPC processes below. So when X wants to talk to Y, it would request to F3 the IPC process. So can I allocate the flow between F3, between me and Y? F3 would resolve the address of Y, so it would be the address of F4, and route within the layer, so there's no layer violation. So it just, F3 resolves the address of F4, which is distributed within the diff. This has to be done in a way, could be DNS. We think that it's more scalable using a distributed hash table, and we're implementing it in that way, so that it knows, F3 knows in somehow how to reach F4, but this is not unlike the current internet. So the benefits are that the application namings ensures mobility and multi-homing, because the mapping is done dynamically. So when Y in this would move to F2, F3 would just again resolve Y, and it would find F2. The timescales at which this happens will be depending on how you implement it. With the DHT, it's not a silver bullet that solves all your problems, but it can be done. Right now, you would do it with updating DNS entries, which also take a lot of time. So it supports QoS in the architecture. There's no need for middle boxes. It has smaller routing table sizes, so because you can have hierarchical addressing in each of the diffs. There's a paper of that by John. Improved security inherent in the architecture, because you have security when you register with the network, when you try to allocate a flow, and you can have security between your applications. So there's different points in the network where you have to authenticate before you can send data, which prevents you from just flooding a certain server, because you first have to find a diff that can access that server, and you have to be able to enroll in that diff. So there's a lot more steps to be taken before you can communicate to an endpoint, especially in private networks. Of course, in public networks, you wouldn't implement all of these features. You need some net neutrality, things like that. So it also allows product and service differentiation to the design of custom diffs. So it's just an architecture. It's not that we say you have to implement this that way, this that way. So you have a lot of flexibility there, how to implement for certain functionalities all these elements in the diff, which allows you to have different, so to have services and products that you can sell which are differentiable, and it has the potential to significantly reduce OPEX and CAPEX. So the project the hat that I'm wearing is for IRENA. IRENA is investigating Rina as the next generation GÉANT and NREN network architecture. And the research question is just, if we use this architecture and we apply it to the GÉANT and NREN case, what are the benefits? So it takes input. This is a little bit of the project structure. So it takes input from GÉANT. So it takes, we did a survey with the NRENs, of which 24 responded, to build a good use case to test Rina on. We also did a SWOT and pest analysis of different network architecture, comparing them to each other, and we are compiling that right now into the first milestone of the project. And then we will apply the Rina architecture to the use case, perform lab trials, and then the lab trials will use the prototype stack that we are building in the Linux kernel in the FP70 RATI project. And then we try to show you the benefits, the possible benefits that Rina can bring for the NRENs. I'll skip this. So some of the future requirements that we're taking into account are that taken from the NREN survey. What came back is that you really want to optimize link utilization, have more security, that this is a major issue for the NRENs, mobility of users, and also that in the future you are implementing more and more cloud services which are going to be more and more distributed. So the current state of the art of Rina, this is a timeline. We are here. So these are the main projects which are currently funded now in Europe. and we are leading the way over the US. So there are some US projects, but at least not on the same scale of Europe. So we have the IRENA project, which is in the Géant Open Call. We have the IRATI project, which is implementing these ideas directly into the Linux kernel to have a performant prototype. And then there's Pristine, which is implementing additional features. So currently, previously there were small lab prototypes. Now we have a Linux kernel prototype that is getting more and more mature, and we are implementing the lab. So interconnecting labs over IPsec tunnels, so we need a diff over TCP. In terms of standardization, currently there's something called the Pouzin Society. It's named after Louis Pouzin, the guy that really invented connectionless networking, who is also really supporting the research. And the idea is to standardize it in ISO subcommittee 6. The IRATI project, quickly, it's developing an open source Rina prototype in the Linux kernel. It will have a public release end of next month. This is a quick diagram of the software that's developed in IRATI, and the main points are here. That we have shim diffs over TCP UDP. We have implementation of the complete normal diff in the Linux kernel. And the management interface is minimal. That's going to be extended in Pristine. And there will be a tutorial and demonstration at IEEE GlobeCom this year. This architecture, you can find it in the March issue of IEEE Network of this year also. So Pristine, my apologies. So the 4 partners in the IRATI project are I2CAT, which is the coordinator, Nextworks, us, iMinds, and Interroute as core partners. So there's a follow-up project called FP7 Pristine that started January this year, which is going to implement, so IRATI is really building the very basics of the car, just the steering wheel, the wheels, the brakes. But Pristine is going to add a lot of features: security, QoS congestion control, protection and resilience, multi-layer management, and it's also going to develop a first SDK so that people who are interested in technology can get their hands on it. There are a lot more partners in Pristine, so we have more industry support from Ericsson, from Thales. Nexity is a small company providing distributed cloud services. Atos, Juniper, this is University of Oslo, which is looking at congestion control. So the guy there is Michael Veldt, who is the congestion control research group chair. The University of Brno, Telecom Sud Paris, CreateNet, and iMinds. Telefonica, of course. So the adoption strategy. So, okay, we have an architecture, it looks very nice, but how are we going to get people to use this? People aren't even using IPv4, which should be, it's 20 years old. So the advantage of Rina is that you don't really need flag day, so you can just adopt it. So what is developed in the IRATI project is that it just runs over Ethernet. So if you have an Ethernet network, you just run the stack locally, and you can build on top of it using Linux machines. And then hopefully, the idea of IRATI was to get the stack into the Juniper Junos. We couldn't get access to Junos because Juniper wouldn't allow us. But the next version of Junos will have NFV type of components, so that it would be possible to run our Linux stack inside a Juniper router. And the end goal would be that you just have physical media which directly supports the IP API. So the question is, are you ready for a simpler future where you don't have a lot of all these different technologies, but just a number of diffs together with different policies to build the internet of the future? Thank you. So I'd really recommend looking at these sites of the IRENA project, the IRATI project, Pristine project, and there will also be a tutorial at GlobeCom. Thank you.
Thank you very much for your excellent presentation and challenging, I would say. Any question from the audience?
Yeah, Stefan Winter from Restena. I'm just wondering, you're very early in the process, so maybe it's a bit unfair to ask this now, but do you have any idea if this can actually scale to internet-wide use? Because so many entities have to find each other, discover each other, and move along. So how does it scale?
It scales like a DHT. So the scalability depends on how you implement the functionality of discovering all the applications on top. Because you have multiple layers, you would have hierarchical routing, which really reduces routing table scales, but finding the nodes is the similar scale as DNS, where you also have to find Google and resolve it to an address, internet scale. So, and we think that a distributed hash table would be a lot more efficient than the current DNS solution, and that's what we are implementing.
You began by motivating this architecture by referring to the problem of nodes not having addresses. I'm not sure how central that is to the problem statement, but if it is a central element of it, I'd suggest using as a baseline for comparison the idea that a node can be given a virtual address on a loopback interface, and then you have a model in today's architecture which gives addresses to nodes, and you can compare it with your new architecture and identify whether what the benefits are.
Okay, that seems.
It's not something you've thought of already.
Well, it's one of the issues, but we think that that's just the mapping of the so. Currently, you're always routing between interfaces. So even if you have the loopback address, you would be routing to the interface and not to an application. And what is very important for the assumptions that are required for Rina is that you route to applications because they can move. So if you have a data center which has some virtual machine and you move it from one physical machine to another, it just has a new mapping in that DHT system. So that's something that would still be...
That's what you get with loopback addresses, and it's widely used for anycast purposes already. So maybe we should talk over coffee.
Okay.
May I have yes.
You're just saying about the mapping of the application to the address and how it can move. And you were likening it to DNS and DNS lookups and the like. How would you ensure that in the case of a rerouting, that happens quickly enough that the application is able to reroute in fractions of a millisecond, as it were?
I think it would be just the same as we're doing it right now. I mean, it's just an architecture. So this is a problem that will arise in every network architecture. So it's not that every that Rina has a solution to every problem that is a lot more advanced than what we are doing right now. It's more how you arrange the components makes things simpler to implement or to do. So when your node reboots, you would have to re-register all the applications running on that node. So especially restart all the IPC processes on that node, registering them again with the diff. So that's definitely a problem that we should look at. It's not only the application on top.
May I have a question? Connection to Stefan's questions. Looking at the adoption of the slow adoption of IPv6, what do you think about the ultimate adoption regarding the application rewriting and also the changing of the mindset of the networking persons to accept your ideas, this recursive network architecture changes to happen? What is your assumption?
Well, I think in the end it will boil down to one thing, and that's the green stuff. Will it be cheaper? So currently, why is IPv6 getting slow adoption? Because it's giving you exactly the same service as IPv4. It requires you, maybe a little bit better, but it's not. It's a technologically more advanced solution that gives you nothing really more to your customer than you already have. And the technology for having more addresses is now becoming more stringent. Now people are adopting it out of necessity, but what we'll have to do is just show that Rina can reduce your operational expenditures, reduce your capex, and then people will start adopting it. It will boil down to the cost of the solution, not whether is the technology better or not. Can people make money out of it? Okay. That would be my response.
Yeah. Okay. Thank you very much. Your presentation. And if there is no more question, then we will move forward to our third presenter, who will be David Wilde, who began his career at computer networks in late 90s at University of New South Wales. And since then he worked in a variety of technical and managerial positions for telecommunication operators and service providers across Australia and Europe. David Wilde is working for ARNet at the moment, where he's responsible for network architecture. He's interested in ensuring that ARNet reaching the forefront of the technology, engaging the both vendors and other NRENs across the world in order to better support research and educational networks. He will present how the global research and education networking should look like in the future. And David, please give your presentation.
Thank you. How's everyone going? The third session of 3 is always a bit of a tough gig, isn't it? You're falling asleep out there. Do you want to stand up, stretch? Anyone? No? I love this microphone. I feel like I'm in the FBI. I should have sunglasses or something. Right, so my name's David Wilde. I am from ARNet, Australia's research and education network, but I'm not here representing ARNet as such. I'm actually presenting on behalf of. Thank you. Presenting on behalf of a number of people, and if you've had a look at the paper which is on the website, you'll see there are about 10 or 15 network architects and similar people from around the world who've contributed to this. What I'm talking about is it's by no means as detailed as my preceding two presenters, who are obviously way more qualified than I when it comes to the depths of the bits and bolts of networking. But this is much more high level. It's some work that's been going on over the last several months now, called the Global Network Architecture, and I'll explain what that is, where it's come from, and I guess where it's going to. So a number of us here work for NRENs. ARNet's an NREN, Janet and SurfNet and RNP and so on. Most countries have got an NREN. And over the years, I guess we collaborate more or less. I would say we collaborate better than commercial telcos generally, but we probably don't collaborate as well as we could. And so, in an attempt to address this, a number of NRENs, Internet 2, Surnet, NordUnet, and Janet got together, or their CEOs got together, probably over a beer at some point, as far as I know, and said, "How can we do this better? How can we collaborate better with an intention of bringing out services better?" And so they created the Global NREN CEO Forum, which is currently a group of 15 CEOs. Based on the G20 model, so presumably they're not so good with their maths. And the idea is that it addresses this question of collaboration, and I guess more concretely is an attempt to bring out services and various other initiatives in a coordinated manner. I guess sharing resources, because at one level we're all doing the same thing, and maybe pulling together our weight as a larger group when it comes to negotiating with vendors and such like. So there's the goal: seamless global services delivery for users in RNE. I guess the aim is for us to better serve our users, so the universities, the schools, and so on. So that was created a couple of years ago, and of that, fairly rapidly came 4 initiatives. One of them, and there are various people talking at this conference about various other of these initiatives. One of them is Global Real-Time Communications Exchange, so that I can pick up my soft phone, or however it is that I pick it up, and call somebody at MIT, and I get video popping up for instance. Another one is global services delivery. So that's maybe related to Internet 2's Net Plus project of pooling our resources when it comes to negotiating products. Federated identity management, so that we're not just all acting as independent little pools. We actually do talk to each other at a technical level. And the fourth one is what I'm talking about today, which is the GNA, the Global Network Architecture. So if I focus in on the GNA, this is where it's come from. The intention really is to see how we as NRENs can work better together. So when you need a service from Jive in the Netherlands to CSIRO in Australia, today it's a pretty laborious process. I call up Internet 2 and they call up Canary and then they call up SurfNet and we string it together, and sometimes it works, sometimes it doesn't. When it stops working, it's very hard to put things back together again. So this is an intention. The intention is to see how we can work better together. And it came from an initial sketch by Professor Lee from CERNet and Jim Williams from Internet 2. So what is the GNA and where's it going? Now I should probably precede this by saying this is very much a work in progress, and it will be for some months. Partly a group of people working on this and reporting to the CEOs and soliciting to a greater and greater degree your input, and because we're not sitting in a box trying to design something which then we find out that nobody wants. The intention is very much that this is something that's collaborative. This diagram always launches a lot of discussion for various reasons. For instance, Singapore has kind of drifted into the highlands of Indonesia in this diagram, and on Australia there, I don't think would be wanting to connect Darwin, which is possibly the most remote spot you can possibly find in Australia. But this is an artist's impression of what a global NREN network might look like. The important part of it really is adding in connectivity between NRENs and regional networks. And there are red dots spread around there which form some kind of exchange point where NRENs and regional networks can connect into that. What are those links? Well, I'll talk about that in a moment, but the intention is, as a group of NRENs worldwide, we can become aware of and negotiate better with, I don't know, a cable operator when they're putting in a new service from Perth to Singapore, for instance, or, sorry, my example's always very Australian focused here, or from, I don't know, Cairo to somewhere else, get in at the ground level, get spectrum, rather than today where we're each buying, say from Europe to the United States, we're each buying our own 10 gig circuit, and before you know it, you're spending 5 times more than you could. So that's kind of an end goal, I suppose. How is that being organised, and what's actually going on right now in this space? So the CEO Forum created the GNA Action Group, and that spun off 2 activities. One is a technical group, so that's a group that I'm part of. Co-chaired by Erik Jan Bos, who's over here and whose slides these essentially are. So any errors come from me, all the intelligence comes from Erik Jan, and you can fire questions at him at the end. And so that architecture group came up with a sketched up architecture, which was presented to the CEO Forum about a year ago or 6 months ago, and that was generally well received, and then they gave us a whole bunch more homework to go away and work on. In parallel with that, there's a subgroup of the CEOs who form the executive action team, and essentially their job really is to take information produced by the architecture group and use it as collateral when it goes to talking to funders or talking to grant governments with grant money and so on. So the idea here is to come up with a technical framework and feed it into these CEOs and try to get some kind of traction that way. Most importantly, I suppose, to be going to European or American or Asian or whatever funding agencies and presenting a unified front is what it comes down to. And I'll talk a bit about how the architecture group is what we're working on, but broken down into 3 groups there to try to be as organised in spitting out something useful as possible. Obviously today, around the world, there is a network, right? I can download stuff to Melbourne, which is sitting on a university network anywhere around the world. So something exists, and we're not talking here about again, sitting in an ivory tower and coming up with a great plan to replace a whole bunch of stuff which exists and works really well, both at a technical, as in there are cables and circuits that work well, and there are organizations and approaches that work well too. For instance, Dante or NordUnet, for instance, group a number of organizations together, and there's some really valuable lessons there. But the intention is to take where we are today and try to identify how it could be better and move towards that. So there's an ever out-of-date diagram of what the world's internet looks like. I know it's out of date because today I've got network engineers in New Zealand in the very bottom right corner there connecting a red line to there which didn't exist yesterday. So I guess that's the nature of these diagrams. They're always out of date by the time you put them into presentation. So the intention is to start with what we've got, overlay onto that, I guess, identify where the big science and big research requirements are today and going forward, because that changes too. The SKA telescope will appear. The LHC is an existing one. There are others who will be added. We can anticipate that to a certain extent, and then learn from the RNE networks that make up this world, and take the best of as many of them as we can. The intention is to come out with a coherent or cohesive, if you like, set of big bandwidth pipes all around the world. I guess that's the ideal for all of us, isn't it, really? To have lots of bandwidth, but then a flexible set of guidelines and provisioning and operating systems to layer on top of that, to be able to provision services more easily from anywhere to anywhere. So that's the bit that perhaps we don't have today and which we would really like to move towards. With the ability, therefore, to overlay networks on top of that. And that could be a testbed network, so that you can simulate the internet with devices sitting in Australia and the States and Europe. Or maybe something like the LHC1 network today, interconnecting sites which have large data transfer requirements. All of this, the intention is to have the flexibility to overlay that on top of this. I got ahead of myself, didn't I? And I guess you can download these slides and dig into this if you like. This is more a visual view of what that might look like. And obviously, in trying to, I guess we're aware of this anyway. The reason that when I want to get a circuit from Melbourne to the Netherlands, that it's difficult, is because there aren't systems in place to talk between these networks. It's a very manual process. There's work being done on NSI protocols and other dynamic circuit type things that could solve that problem, and that's the kind of thing that we'd like to move towards, is how you turn a bunch of islands that touch each other in the form of NRENs and turn it into a cohesive whole. Clearly, whilst it would be nice for some mysterious funding agency to come to the Global CRO Forum and say, right, here's $50 billion, go ahead and build yourself a great network. And I've got colleagues who'd love to buy cable ships. I'd be quite happy with that notion myself. That's not going to happen. So the intention is to identify either where it's easy to consolidate stuff, and maybe that example of, and I'll talk about this in a mo, the transatlantic connectivity is an example of that. Try to consolidate a bunch of separate connections into a couple of very big ones. Another possibility might be in less developed areas of the world, maybe there are cables being built, but the local NRENs don't have the financial clout to be able to get on board with that. Whereas if there were like 3 or 4 bigger NRENs involved who could say, well, actually, it would help us to be able to get to Bangladesh or to the west coast of Africa, maybe we'll chip in some money or we'll come to the table. That's another potential low-hanging fruit, which helps in a completely different way. The more important thing, I guess, out of this, and this is the nature of the global aspect of it, is that whilst this has come from the Global CEO Forum, which is 15 CEOs from 15 NRENs, the intention very much is that this isn't focused on making sure that Europe and the States can connect really well together. The intention is that the entire world can connect to each other. And personally, from AARNet's perspective, that's fantastic, because we're trying to connect an increasing number of schools and universities in Asia, and bandwidth to Asia is generally a nightmare from Australia. So that notion of bringing regions up whilst at the same time assisting the bigger areas of the world is certainly the intention. As well as trying to stay ahead of the curve. So today we've got the internet, and it kind of works and it kind of doesn't work. in the research and education space, there's a massive work going on from people who are gathered here today and all across the world on how we can make the internet better. And incrementally, there's the potential there for us to do things a bit better. Our research and education network doesn't have to just simply mimic the internet. It can be better than that, and we can progressively work towards that. I mentioned before that potential low-hanging fruit, that notion of replacing a bunch of 10 gigs across the Atlantic Ocean by some bigger pipes, and I guess it's not really a GNA pathfinder as such, but it certainly can be treated in this way. There's the ANA 100 gig project, which was initially 100 gig from Netherlight to Manlan, a very creative way of deploying a network in that the electronics are run by the NRENs as opposed to just buying a circuit, which is traditionally what cable operators want. That's turning into already a more production-based service with resilience or redundancy. And I put the lines on here, so in the same way that they were possibly wrong in that other diagram, they're very likely wrong in this diagram. I'm fairly sure that that blue line doesn't run through Scotland. It's probably submarine rather than where I've drawn it. But artist's impression again. But we can see already that there's, and this is more a mission of discovery too, how do you run a pair of 100 gig links when there are 6 organizations down the bottom there with very different needs and different capabilities to contribute and different things that they want out of it. It's in that sense it's very much a pathfinder, and I think our intention is to move towards more of this to learn on the fly as we go. So where is the GNA going to? So today the architecture group is working on adding a bit more detail into that artist's impression diagram. We'll probably put Singapore where it's meant to be, and maybe even include some potential architectures, technical and organizational, operational, and what services will be offered, and try to turn that into something that you can read and say, okay, so this is what the GNA is going to provide, and this is how it's going to do it roughly. The hope being, of course, that that's going to match fairly well with what universities want and what our users want and what big science wants. And we have to provide some feedback to the CEO forum by the middle of this year. And then that gets fed into the executive action team, that second group that I mentioned, who will begin at that point the process of feeling out funders and cable operators and seeing how we can take that material and turn it into a reality. More importantly, at this stage, I suppose, and this is why I'm standing up here representing this group of people who've been working hard, is to communicate this and consult to hear what will be useful, what wouldn't be useful. We've presented this at the Internet 2 meeting. I'm standing here at TNC. There are potential for talking about it at various network architect workshops, and for those of you who would like to come for a trip down to the Southern Hemisphere, there's a Glyph meeting in Queenstown in New Zealand, which is a lovely place to come to at that time of year. And so our intention is to keep consulting and understanding what the requirements are and how best they can be filled. If you'd like some more information, Internet 2 has put up a bunch of info on their website, along with some contact details, I think, of Eric Yowen and G. Williams, so it's a good place to touch base if you would like to. That's it from me. There's my email address if you would like to talk to me as well. Thank you very much for surviving.
Thank you very much for the presentation. Any questions, comments from the audience? Maybe I have one then. Sure. Can you comment of the different usage policies of different regions? How can you overcome with that one?
Different what sort of policy?
Usage policies, like who can connect, what are the service model, funding model, how can you cope with that one? Or can you comment what's your ideas behind, how can you resolve such a problems in GNA?
It's a fantastic question. Or
do you have any ideas?
Sure, we've certainly got lots of ideas. What it throws into stark relief is the fact that the technical side of things is usually the easiest way, right? Regardless of how complex technical requirements are. You might want open flow access to the network. I might want production level VPNs. That's kind of easy to solve. You just configure up routers and switches and they work. That question, in fact, it's at the one side it's usage, who's allowed to do what on a network. On another side, it's funding. At ARNet, for instance, we're funded by our customers paying for services, whereas at Canary, for instance, they're funded by the government giving them stuff. And I'm sure that the Canadian government doesn't necessarily want part of their funding to be going towards paying for links in Southeast Asia. At this stage, there's no answer to that. The simple answer really is, I suppose, that in treating this as a collaborative effort between, like, at a CEO level and then at a technical level as well, there's hopefully more possibility of presenting a common front to funding agencies, so that instead of...
So maybe you harmonizing your ideas together and approaching all the necessary agents.
It's true. As well as, in reality, it is going to be very much on a regional kind of basis too. You know, the requirements within a region are going to be quite different to another region, and so maybe if it doesn't work to have everybody with the same approach, then let's break it down by region or even by country, case by case, if it needs to be. But you're right. It's whilst it's an attempt at coming up with a global solution, it's certainly not going to be identical everywhere. Yeah.
Okay. Any question? Yes.
The next question has to be down the front, and then another one up the top, just to make Janos run.
and I'm sure to add to the symmetry. I'm Simeon Mitev from the South African NREN. So my question has the context of a continent of 1 billion people that's not part of the global CEOs forum. So the question is really regional consultation. Is there any plan around formalizing that, or is it basically GLIV meeting TNC?
No, there is. In fact, Eric Jan can maybe answer and talk about questionnaires and such like.
Thank you, Simeon, for this question. Two remarks. First of all, there is a person from Africa on the CEO forum. I think he's here, actually, not in this room, but at this conference. It's Tusu. In the South Africa, the Cape Town meeting, Tusu participated, and even Boubacar Berry from WECRAN was present by video link. So we are engaging with Africa for sure. A group was established, one of the other 4 groups. There are now 8 groups functioning under the CEO forum. These are the challenges groups that David mentioned. There are 4 more study groups. One of them is the knowledge exchange group, in which well-established NRENs wants to exchange knowledge with the developing NRENs. Not to transfer information in one direction, to make sure that we have information flowing in both directions, because we quickly learned in Cape Town when we met there in December 2013 that the starting NRENs, the developing NRENs, do a number of things quite differently from the well-established NRENs, because they jump over a lot of things that we had to worry about and they don't have to worry about. For instance, the mobile usage in Africa is completely different from mobile usage in Western Europe or North America. And the way that mobile is used in Africa is really inspiring for the NRENs that are from the developed countries. So there's a group now dedicated to that topic. That group quickly met in Denver at the I2 Global Summit. And there was a request from Boubacar Berry to participate in the Africa Internet Summit 2014, end of this month, early next month, in Djibouti. And the story that David talked about, the GNA that David talked about, and the larger picture of the CEO forum, the 8 groups under it, especially the knowledge exchange group, will be presented there. I will be traveling to Djibouti and I'll be delivering the story there. That's on the Monday, June 2nd, where the AFRAN meeting is organized.
And
so that's a long answer to your simple question. Sorry.
At the same time, Jim Williams went to the APAN meeting to talk to the Asian region, and no, certainly the intention is to to engage with every NREN, ideally of all 120 of us, or however many there are now, and ensure that what each of us needs is included in this as a set of requirements.
Any other question, comment? Then I will give thank again.
No worries. Thank you.
Good presentation.